wrote lambda majorizes gamma, and this is fixed, this is correct. And there was that typo that was confusing me because it didn't make sense. Anyway, this is correct now. Gamma majorizes lambda if the sum's going downwards. We always start with this ordering. If the gamma is bigger than the one for lambda. And, okay. And I also want to say one other thing. LOCC means not only local operations, but classical communication. So if Alice does something on her end, she's allowed to communicate this to Bob, and then he can do a local operation. So they can keep going back and forth. No matter how many times you do it, you have to satisfy this condition in order to map finally from one state to another. Okay, so that's a little bit of an explanation there. Now we'll go forward. Now, I want to discuss the operational meaning of entanglement, and I want to discuss this from the point of view of statistical mechanics eventually. So, suppose Alice and Bob have n copies of an entangled state. I remember the goal somehow is to measure entanglement in a very primitive sense in terms of Bell states. Keep that in mind. And in order to do that, we imagine that Alice and Bob have n copies, and they're going to try to produce these n copies in terms of a certain number of copies of Bell states. That's the goal. And by measuring how many Bell states it takes to make the density matrix you've got, or how many, or the other way around, is a measure of entanglement. How many maximally entangled states fit into the given state you've got. And in order to do that, we take many copies of the given state and try to compare it with many copies of the Bell state. Okay, so suppose Alice and Bob have n copies of a state, their pure state. Now this is pure states now because I want to use Nielsen's theorem. How many copies of a Bell state, say psi plus, for example, can they produce from it using only local operations in classical communication, LOCC? Conversely, to produce this state, here it is, to produce it from a stream of Bell states, m of them, using local operations in classical communication, how large does m have to be? So there are sort of going to be two measures of entanglement, the n versus m, going one way making Bell states or using Bell states. These will be two measures of entanglement. Now, these are measures of entanglement that are somehow fundamental in a certain sense. And the object is to relate that to entropy, which has been used to define the entanglement up to now. But you can ask the question, what's special about entropy? Why do I use entropy to quantify entanglement? Well, that's because in figuring out this problem of making entangled state out of my state or the other way around, I will be led to an entropy problem. And that's how entropy gets into the story. Okay. Now, in the large n limit, one can define, and I'm just repeating myself here, one can define two operational measures of entanglement: distillable entanglement, called ED, and entanglement cost EC, that quantify respectively the rate at which one can distill E bits or Bell states from psi 1 to the given psi, and how many E bits does it take to build psi 1 2. Both are shown to coincide with the entanglement of formation, EF, that we defined before as one measure of entanglement, and it's the one you're usually familiar with. You take a state, a pure state, it's what we're talking about now. You take a pure state, you trace over half of the state, and you look at what's left and see how much entropy is in there. So it will turn out that this cost of making Bell states out of my state, or my state out of Bell states, is going to turn out to be the entanglement of formation, which we defined before. But this is only for pure states now. Yeah.
What do you mean? What is the rate at which one can distill E bits?
Well, because it's a rate, because n is going to go to infinity. So I'm taking, rate is, forget the word.
Okay.
It's just I want to take n copies and break them. See, if I just look at one copy, I mean, I've only got two variables. It's sort of hard to figure out how many Bell states is in there. So that's why I take n copies and compare that with m copies of pure Bell states. And it's that comparison that the situation for mixed states is much more complicated. It was conjectured that the entanglement cost was the same as the entanglement of formation, but this is now known to be false, although no explicit counterexamples are known. It's again one of those things. Hastings. It is easy to prove that the entanglement cost is less than the entanglement of formation. And it is conjectured but not proved, and here's a very fuzzy statement, that the entanglement cost equals the entanglement of formation in most cases, whatever that means. We don't know yet what most cases means. But anyway, I leave that for the future. Right now I'm talking about pure states, and there we do know the answer. Okay. So, so Alice and Bob have a state rho 1, 2. They make, in principle, a large number of copies of this state, form the n-fold tensor product. These are just independent. And they ask if they can find an LOCC that maps n prime copies of a Bell state into this given state, into n copies of the given state, and try to make n prime as small as possible. Now, it doesn't matter which Bell state we use here. I wanted to clarify that point, because remember, among LOCC, there are unitary transforms. So if you can do it with one Bell state, you can do it with any Bell state, because the two differ just by a unitary. And so and that's an LOC. That's a local operation. Now, to be honest, Alice and Bob have to produce n prime copies to within a small tolerance. And they're not going to make it exactly equal, but within a small tolerance, which technically will be within trace norm or some other norm of this kind. Up to some small tolerance, we hope that we can produce the state. Now, so we define the entanglement cost as the limit as n goes to infinity of this ratio, and how many Bell states divided by how many copies of my state, Alice and Bob's state. And it's also the limit of the entanglement of formation divided by n for n states. And this is going to be what we're going to show. As mentioned above, EC equals EF for pure rho 1, 2, and EC is less than or equal to EF generally. For entanglement distillation, on the other hand, we do things the other way around. We LOCC map a product of n copies of rho 1, 2 into n prime Bell states with n prime over n as large as possible. Then this is equal to the limit of n prime over n. And in general, of course, the ED is less than or equal to EC. You can figure that out just from the logic. There's no deep theorem here. Okay. All right, so the connection between entropy and entanglement. So you may wonder why entropy plays such a dominant role in the quantification of entanglement. That's what I said a few moments ago. For pure states, we can use Nielsen's theorem to make this very clear to anyone familiar with elementary equilibrium statistical mechanics, where the difference between energy and free energy is T times the entropy by definition. And this entropy in statistical mechanics is, of course, given by this familiar formula minus the sum of P dot P. So we're going, that's statistical mechanics. So a Bell state remember what it is. It's up, up, plus down, down, divided by square root of 2. If you compute row 1, the one system density matrix, well, you get 1/2 times the identity. So in other words, since we're on C2, the spin space, spin up or spin down, both become equally likely if you just look at one system, one particle, if you like, when you trace out the second one. So the two eigenvalues of the density of the row 1 density matrix are 1/2 and 1/2, adding up to 1, of course. Now the eigenvalues of the n-prime tensor copies of this Bell state, which has this much dimension, right? The dimension of the Hilbert space of the tensor product of C2 n times is just 2 to the n prime. N prime times is 2 to the n prime. They are easily seen to have only the eigenvalue 2 to the minus n prime. You just multiply 1/2 n prime times. And this occurs with multiplicity 2 to the n prime. So if I take n prime copies of a Bell state, the spectrum, looking at row 1, is the silliest spectrum you could imagine. All the eigenvalues are the same. There are 2 to the n prime eigenvalues, and they're all the same. And they add up to 1, of course. It's dull. So this is a maximum entropy state. The entropy is log of whatever, 2 to the n prime. So divided by n. So now suppose Alice and Bob share a pure bipartite state of dimension d squared. D is not necessarily 2. And let lambda j denote the set of Schmidt numbers, which we talked about before, which of course are the eigenvalues of row 1 for this guy. And these are called lambda 1 up to lambda d. Okay? Now we make n tensor copies of row 1, 2, which is a pure state, of course, because row 1, 2 was. And, and we look at row 1, the thing you get after tracing everything out, and that's, of course, still a tensor product. And it's equal to the n-fold tensor product of row 1 to the nth. Row 1 was what you got from row 1, 2. And the eigenvalues, what are the eigenvalues? Well, each eigenvalue is a product of Schmidt numbers, one from each factor. So you have this list of d Schmidt numbers, adding up to 1. You have n copies. So for each copy, you pick one Schmidt number and you multiply them together. That's the eigenvalue of row 1 to the nth. And so I have lots of things. I've got a box with n marbles, n-colored marbles in it, and I want to know what kinds of products I can make out of these things. And if you know anything at all about statistical mechanics, you're going to guess that most of the time when I take this product of a whole lot of copies, the product is going to be more or less the same. Right? That's kind of statistical mechanics. I don't expect to get a very tiny product or a very big product. In fact, they're going to be more or less to within small errors, all the same. And that's what we're going to look at. So let's go on with that. All right, so now think of a stat-mech problem of n independent particles with one-body eigenvalues minus log lambda 1 up to minus log lambda d. Remember, these are the Schmidt numbers at inverse temperature beta equals 1. And the partition function is just, you sum the eigenvalues for each factor. These are non-interacting particles with d possible states, if I can put it that way. This is just an analogy, of course. There's no physical system here. And so the partition function is just the sum of the lambdas to the nth, and that adds up to 1, so it's 1. Which means the free energy of this system is 0, because it's the log of z. And we can compute the entropy per particle, which is always minus the sum p log p, which is minus sum lambda log lambda. Now, we used the Boltzmann factor to do this computation as e to the minus the energy, namely e to the log lambda. which sums up to 1. And we did not use e to the log 1 over d as you might wish. You see, you might say, I'm picking these d numbers at random, so the basic probability is equal for each of the numbers. But that's not right, because I'm interested in looking at the trace of what I get. So I take as the basic probability factor, not the constant 1 over log e to the 1 over d, but I take lambda, because the small lambda should count less than the big lambda. Okay. So we do that because we're interested in estimating the errors in the trace of row 1 caused by perturbations, and not in trace of d to the minus 1 times the identity. Okay, so we imagine a system with these energies, n copies of the system. Now in this problem, the average energy per particle is just E equals S, because the entropy is 0. The free energy is 0. Free energy is E minus S. T was 1. Now physics, actually the law of large numbers, that's really what's going on here, the law of large numbers, also known as, there are fancy names that go in this field. One of the fancy names is the asymptotic equipartition theorem, but it's been known to the ancients as the law of large numbers. Okay. This tells us that the distribution of the n-body energy values is sharply peaked around n times E. Right? So this is what I said before. We know from physics, statistical mechanics, that the distribution of this product of things is going to be, they're going to be all the same, and they will hover about the number n times the average energy, the energy being log d. Okay, so except for a small probability, that is to say, by small probability I mean a small change in the trace, all the eigenvalues of row 1 lie in the interval e to the n times minus the entropy, minus epsilon, or e, whoops, something went wrong here. One of these is plus epsilon, sorry about that. For any epsilon positive as n goes to infinity. Now since the trace is 1, there are between this many and that many eigenvalues in this interval. So the eigenvalues of row 1, when you multiply these numbers together, live in a very tiny band, and the number of eigenvalues in this very tiny band is e to the entropy, the total entropy, which is n times the one-body entropy, and the eigenvalues are e to the minus that, adding up, of course, to 1, which is what it should add up to. Now, I want to dwell on this a little bit because sometimes there's some misunderstanding. The eigenvalues have not disappeared. There are d to the n eigenvalues, because that's the dimension of the space. So there are that many eigenvalues. But almost all of the significant ones are in this interval, and the value of these eigenvalues is likewise very close to the number e to the minus ns. And where are the other guys? What happened to them? Well, they're down at 0. I don't see them because I'm measuring them. I agreed to measure them in terms of the trace, or in terms of the eigenvalues themselves, and they're very small. So in terms of taking the trace, they're just not there. They really are there, but I don't see them. Okay. So these are the eigenvalues of interest. So what do I learn from this? So let us summarize the situation. Whoops. Oh yeah, there it is. It's getting a little weak. You got a battery or something?
You want another one?
Well, yeah, it may be because I can hardly see it. In fact, it's giving up the ghost. Yeah. You got another one?
Yeah.
Good. Okay. Good organizer. Okay. So if we have n prime Bell states, the non-zero eigenvalues of rho 1 n prime is exactly 2 to the minus n prime, thank you, and that's the degeneracy. So that adds up to 1. The non-zero eigenvalues of rho 1 to the nth for our pure bipartite state, n is different from n prime, lie, except for vanishingly small number in terms of the norm, in terms measured as eigenvalues, is somewhere between this value and with the degeneracy e to the plus that number, and e to the minus this with that much degeneracy for any epsilon positive. I don't want to take epsilon 0 because I don't want to tell you it's exactly this number, but it's in a very tiny band. And I can make that band as tiny as I like as n goes to infinity. Okay. So the entropy of rho 1 to the nth is that's n times s, with this being s. Okay. So you believe this from statistical mechanics. It's really the counting of products, independent products of independent numbers. Okay. So Nielsen's theorem tells us that we can find an LOCC map from Bell states to our pure states if the spectrum of this guy majorizes the spectrum of Bell. So this occurs if this many states is bigger than what? Are you fixing it? Oh, thanks. Okay. Oh, wow. Look at that. Which is, of course, 2 to the n prime. Conversely, we can LOCC from our rho to Bell if e to the n times s plus epsilon is less than 2 to the n prime. So the majorization goes the other way. Now these two conditions look the same. They are the same. So we conclude that since epsilon is arbitrary, we can first take the limit n goes to infinity and then epsilon goes to 0. As n goes to infinity, the two conditions coincide, and we conclude that the limit of n prime over n in both cases is the same regardless of which direction you go in, and therefore EC equals ED, and that's equal to the entropy divided by log 2. Where did the log 2 come from? That was the entropy of the Bell states. This is the entropy of our state, Alice and Bob's state. That's the ratio of the n's, is the entropy in the limit. And that is equal to the entanglement of formation divided by log 2. I seem to have gotten a log 2 somehow. Yeah, that's because in this business, as I said before, yeah, I should have said it. I said it several times, but I'll say it again. Usually one uses the base 2, in which case log 2 is 1, and therefore my former statement that this thing equals that thing is correct if I'm using logarithm to the base 2. But perversely, I'm using logarithm to the base e, so I have to modify my previous statement. There's an extra logarithmic factor in there. That's just because of e is not 2. Apologize for that. Okay. So I hope this makes sense, that entropy comes in if you count, if you take a large, I'm sending this message many, many times, and I take n copies of this message and I look at it, and I compare with the message that I would get with a certain number of Bell states. And I want to get the same entanglement. Then I need the ratio of the number of copies I need is this. And that is a measure, if you like, of the cost of entanglement, but it also relates it to the entropy. That's how entropy comes into the story. It's not put in there just for fun. It really comes out. Okay? Now, let me, have any questions about that? You're tired. It's been a long week, right? Okay. Questions coming?
I want to understand a little bit what it means to majorize the spectrum of the Bell states in the case where they don't have the same Hilbert space.
Good question. You see, the sums have to be the same, but there are fewer Bell states they have, or more, whatever. There are a certain number of Bell states and a certain number of states for my guy. All right, they're not the same. All right, so I just fill up with a whole lot of zeros. So I bring them to the same dimension. And if you interpret Nielsen's theorem in that sense, it just, remember, you start numbering from the top down. And then if you're missing some dimension, you just put zeros in there. As long as the sum is 1, that's okay, you can do it. And the theorem. Okay? Any more questions? Yes, sir.
Just kind of a technicality, but when you're writing the balance for the entropy, is the epsilon inside the parentheses or outside?
Can you speak louder? Sorry.
When you're writing the bound for the entropy of the composite system, is the epsilon inside the parentheses or outside the parentheses?
I'm sorry, I can't understand what you're saying.
You're saying, like the entropy of the composite system per particle or something is.
Yeah,
like
it's n times, yeah.
Or the entry is like e to the minus n plus epsilon to e to the minus n s minus epsilon.
Yeah.
But if you take n to infinity or keeping epsilon finite, then that becomes arbitrarily big.
It's inside parentheses.
Yeah, but I'm taking logarithms, is what counts.
Okay.
Remember, to make the two equal, one is given by e to the n times with a plus or minus epsilon. The other guy is log 2 to the nth. I want to compare the ratio of the two. So I'm really looking at the logarithms when I do that.
Okay.
Okay? I mean, you're absolutely correct. This is always, statistical mechanics. So you're taking a product of a whole lot of independent things. What does the distribution look like? It looks like a very narrow Gaussian, right, for large n. It's getting very narrow and very big. Right? That's what it looks like. And I'm really looking at the position of this maximum and how many states are under this Gaussian. See over here. And up to plus or minus epsilon. They're all in there. Except for the ones that are out in the tails. Okay? I mean, that's basics. That's what we do in statistical mechanics. For good or ill, that's what we do. All right. Good. So now, the next topic I would like to talk about, again, is entropy. But this time it's not about entanglement, although that plays a role. It's something most of you have probably not heard about, but there's a classic paper of Maassen and Uffing, and it has to do with the Heisenberg uncertainty principle. Now, everybody knows the Heisenberg uncertainty principle. The delta p and the delta x cannot both be small. One can be small, but then the other one has to be big, and so on. You all know that. And that comes from the fact that you're looking at two orthonormal bases of the Hilbert space for particles, square integrable functions, but you can look at it either in configuration space or in momentum space as you please. And one can be small, have a narrow distribution, but then the other guy has a fat distribution. All right? And what these guys observed in a physical review in 1988, which is very famous now, is that this was a very general feature about Hilbert spaces and orthonormal bases. So, given a density matrix rho and a Hilbert space and an orthonormal basis, which I'll just call AJ, a bunch of vectors, define probabilities, classical probabilities, as the expectation value of my density in that basis. Okay? Diagonal. That's the sum of the AJ squared. This thing will add up to the sum of this will add up to the trace of rho, which will be 1. So this is a probability. Okay. Now let's define the classical entropy by taking the minus sum p log p, the usual story. So this entropy can be quite small. Even if even if S is, H is this, the entropy of rho remember is a density matrix, the entropy of rho can be quite large. But the entropy measured this way, the classical entropy, which I define this way, perversely, this classical entropy can be quite small. But there is an uncertainty principle. It cannot be too small in the following sense. If I take another orthonormal basis, any other orthonormal basis you like, and look at the classical entropy of the A basis and the classical entropy of the B basis, the same density matrix, then this is bigger than or equal to minus twice the logarithm of the maximum of the inner product of the A's with the B's. So if the A's, if the two orthonormal bases are very, very, very different, then this number is going to be a very small number. And minus the log of that is going to be a very big number. So although these guys can be small, the sum cannot be small. That's what this is saying. Now this can be generalized to continuous bases. For example, delta functions in plane waves, which is a very common thing to do in physics. So if I take my density matrix, compute rho xx, which is the expectation in the x basis, the usual thing, and compute the classical entropy of that. Okay, that would be this that we get from statistical mechanics. And do the same thing in Fourier space. I take the Fourier transform of rho, or if you like, I compute it in an e to the ikx basis. I can do that. And I compare the two. This is positive. That's what this says when taken to the continuum limit. So the entropies on the left can be arbitrarily negative. This thing, remember, does not have to be positive. That's one of the problems with the classical entropy you're introduced to in statistical mechanics, you know, the so-called Boltzmann entropy, I say because I'm not sure that Boltzmann want to push it that far. But if you just take integral f log f with a minus sign, this can go to minus infinity. In fact, will go to minus infinity as the temperature goes to zero, which of course is nonsense because entropy is supposed to be positive. Well, that just means it's a bad approximation. Well, in the same way, this thing can be very negative. But if that happens, this has to be very positive. And they cannot both be very negative because the sum is positive. That's Maassen and Uffing. At least the continuum version of Maassen and Uffing. Okay. Now, Roumain made a conjecture which Rupert, Frank, and I picked up, and we improved this to the following. That this sum, which I just finished telling you is positive, is in fact bigger than the quantum entropy of the rho that we started with, the density matrix we started with. That's a quantum density matrix, so it's got an entropy. And this thing is bigger than that, which of course is necessarily a non-negative number. So it's not just positive, it's bigger than the entropy. So the quantum entropy is therefore bounded above by two classical entropies. Okay. Now, really the most general version of this theorem is the following. If you take two spaces of square interval functions with two measures mu and nu, dx and something else, whatever, dk or whatever, and a unitary matrix connecting one space to the other, with an integral kernel u of x, y, so there's a transform that does this, and you know what it is for x and p, it's e to the ikx, k is k and x is x. So we have, imagine we have this integral kernel for the transform that takes you from here to there. And we define rho hat to be the transform of rho. In other words, it's the rho in the other basis. Then the sum of the two entropies, which I just defined. If you like, this means dx and this means dk, but it's a very general thing. It's bigger than the entropy, as I just finished saying, minus twice the log of the maximum of uxy. Now this looks like Uffing. Remember, Massen Uffing. Remember that on the right-hand side they had the inner product between the two bases. Well, this is what's left of it. This is the same kind of thing. So x and y can be quite different. So for example, x, the first space, can be the integers, and the second space can be the interval minus pi pi. And you recognize that what we're doing is going from a lattice to the Brillouin zone. So the two spaces can look really, really different. Nevertheless, this is true. So that your entropy on the lattice and your entropy in the Brillouin zone, defined completely separately, satisfy this inequality. So that's the uncertainty principle. Yes, sir?
So really, it might be a very stupid question, but
I'm sure not.
I thought I heard you say that the left-hand side can be arbitrarily negative.
Yes.
But isn't minus trace of rho log rho always positive?
No, it depends what the... No, why?
So you're calculating an entropy, right?
The log rho can be very big.
Sure.
So minus...
Big
Yeah.
and negative, right?
Huh?
Big and negative.
No, it can be big, big, big positive.
How?
Hmm?
Aren't the eigenvalues all less than 1?
Hmm?
Aren't the eigenvalues all less than or equal to 1?
No, no, but this is a delta function.
It's important it's an integral and not the sum.
Oh, I see.
Yeah.
I see. So it's just in the continuum limit. Because
Yeah, yeah.
I see. Okay. Thank
Yeah.
you. All right, that helps.
In fact, this always happens in statistical mechanics. You take e to the minus p squared minus v of x,
Right.
right?
Yeah. Yeah.
So that v of x, if v of x is negative, that thing can be huge. And the classical entropy, which you get by integrating e to the minus p squared minus v of x against the log, which is, and you have to divide by the partition function, remember, to get this thing normalized properly. You do all that, that can be very, in fact, it does go to minus infinity as beta goes to infinity. So you go to 0 temperature. That's a fact. They don't tell you this in the textbooks, but this is in fact what happens. Okay. Yeah.
Units
I mean,
question.
huh?
I
Yeah.
have a units question. So the density matrix is unitless, but if I take a position component of the density matrix, that should have units of essentially a delta function of position, so inverse position. How do I take the log of the unit in one?
Well, you should think of it, it's a good question. You should think of it as being very sharply peaked. And that's
Still
what you
has the
do.
wrong units, so there's got to be something, I don't know, position that I multiply it, or I don't know, like the lattice spacing, or something that makes that log.
Well, for this guy, it will be finite. If I just have the integers, then it's discrete, there's no problem. That's the case that's okay. But over here, this could be negative, the entropy on this one. If that was
fine,
your...
because, for example, I set the lattice constant to 1. What's setting the lattice constant as it goes?
No, sorry. I don't understand. What is it?
Maybe it's not.
Yeah, okay.
I think in the inequality, that constant might cancel between the left and right hand side.
Yeah, are you worrying about the dimensional constant? Is that what you're worried about?
Essentially,
Yeah, well, that cancels somehow.
Yeah, the script you was
Okay. So here, in this case, this could be a discrete sum, and this could be continuous. But the fact that this plus this is bigger than that reminds us of this, whoops, I said strong subadditivity. I meant subadditivity. And strong doesn't belong there. That's another typo. I have to fix the typos. Okay. Okay, so now how do we prove this Massen-Uffing thing? Well, what we do is use the Golden-Thompson inequality, the old story. It turns out if you know how to use this thing, you can prove all kinds of useful facts. And the Gibbs variational principle, also known as the Piotrkow-Lyubov inequality, that the trace of rho h plus the trace of rho log rho is bigger than minus the log of the trace of e to the minus h. That says that what Gibbs understood, that's why it's called the Gibbs variational principle. If you want to figure out, given a Hamiltonian, what the entropy and the energy are, you minimize trace rho h plus trace minus the entropy. And that gives you the thing you want to calculate, which is the partition function, which is e to the minus the free energy. So when you take the log, you get the free energy. So prove the theorem or look it up. Anyway, that's another homework problem. I feel I have to give you some homework problems. Otherwise, you'll go home and fall asleep, and you've got to keep working. Okay. Now we come to more serious matters, which are truly quantum mechanical. See, up to now it hasn't been truly quantum mechanical, because what I've done is I've taken a density matrix, taken its expectation values in a certain basis, and then just played classical statistical mechanics with it, but now I want to get into entanglement. So we're going to need this triple matrix inequality, which I keep emphasizing. Now there are several theorems in this direction, but here's one of them. It's the two Hilbert space theorem. So before, remember, we had two Hilbert spaces, which I don't know what I call them, but anyway, position space and Fourier space. So the integers on the lattice and the Brillouin zone, whatever. So imagine you have two Hilbert spaces. Now, by definition, a classical measurement on a density matrix, rho, on the first Hilbert space, is a collection of operators. We had this definition before. It's a collection of operators such that the sum m star m is the identity. I'm doing it the other way around now. Remember, this is not the condition that the trace is preserved. This is the condition that the identity is preserved. And the probability of the measurement m is you take the trace over the trace period of m rho m star. So you get a bunch of numbers this way. That's the probability of measuring m when you have your density matrix. That's basic quantum mechanics. Okay. Now suppose we have our old friend ρ12 on H12, which is just H1 tensor H2. Now this could refer to the same system measured in two different ways, like Fourier space and X space. Or it could refer to two different physical systems. Anyway, we have this tensor product. And we also suppose that we have two kinds of measurements, which are going to go A and B, like measuring position and momentum. And we want to find some kind of uncertainty principle in relating the two kinds of measurements. The measurement operators will be denoted by A and B. So AM, index M, and BN, index N. The indices can be different, of course. So now recall the conditional entropy of this given ρ12 on the space. It's S12 minus S2. And classically, this is positive, I remind you, but quantum mechanically, it can be negative, this conditional entropy. So instead of that, I want to define the classical quantum conditional entropy. Now this is where entanglement comes in. So what I'm going to do is look at the A measurement, for example. It's a measuring apparatus. It acts on the first factor. I take the trace of A rho A, which depends now, it's an operator on the second space. I do it here again, and I take this thing log this thing with a minus sign, that's an entropy. And then I take, to evaluate this entropy, I take the trace over 2. And then, having done all of that, I sum over m, just as I summed over m here when I wanted to, talk about the probability of the measurement. So this kind of quantum classical, it is not the conditional entropy of this measurement. It is not that, because you have to look at where the m and the trace appears in this expression. Now, you might say, well, how did we get into this? What's so good about it? Well, let me, before I tell you what the theorem is, for various reasons, this trying to generalize the Maas and Öfing theorem to this situation, of course, is going to bring in the terrors of entanglement and all this kind of thing. But it turns out that this is a much discussed problem in quantum information theory. And I'm going to tell you this generalized uncertainty principle. So suppose we have two measurements, as I said before, A's and B's, and I measure the entropy, the classical entropy, conditional entropy, which I just defined for you, for measurement apparatus A, and the same thing for measurement apparatus B. And that's bigger than the conditional entropy of the original density matrix minus a constant. And the constant looks very similar to the constant that, if you go think way back to the previous slide, if you take the operator, the B, the A star A, and the B star, you take the trace of that thing, these are all operators on the first space, and you try to ask how big can this be? That gives you a number C, and that's what you put over here. So it's like Maas and Öfing. It measures how, to what extent the two measuring apparatuses are the same, and to what extent they're different. That's what this number measures. Now, if rho 1, 2 is rho 1 tensor rho 2, if it was a very simple case, then this theorem just reduces to the generalized Maas and Öfing theorem that I mentioned before. So it's a generalization of it. The theorem is difficult because it brings out the terrors of entanglement. It was conjectured by Rennes and Boileau in 2009, who realized that the strong subadditivity theorem or some equivalent would be needed. Bertha et al. Proved the special rank 1 case, where all the A's and B's are just orthonormal rank 1 projectors. Then Coles, Griffiths, that's Bob Griffiths and others, and Thomas Michel and Rennes eliminated some of these conditions. All the proofs were very long. It turns out that the theorem can be proved in a few lines by merely adapting the original proof of SSA. That is, by using the triple matrix inequality. There's also a three-space theorem, but we better to stop this while we are ahead. But it's worth mentioning the continuous version of this. So this is what Heisenberg's uncertainty principle becomes when you get entanglement. And here is the continuous version. So we can now formulate the entangled version of the Maas and Öfing theorem, which relates classical entropies in Fourier in configuration space. This is done by allowing the measurement operators A's or B's, indexed by discrete m and n, to become indexed continuously. So it's like taking Fourier transforms or something. That's what we'll do. The sums are replaced by integrals in this case. For the Fourier transform, for example, we apply the two-space theorem and infer that HA plus HB is bigger than the conditional entropy of my state. And what is H space? So now, here's X space, and HB is Fourier space. So here's what I do. I take my rho 1, 2. I take it in an X basis on the first space. I take the matrix element. Then I take the trace over the second, so I do that, sorry. Then I take the log of the same thing. And then I take the trace over the second space. And then I integrate dx. Yeah?
What's the definition of
definition?
Sorry?
What's the intuition for this definition? I mean, HA. I mean,
What is the reason?
intuition of, I mean, what's that?
Okay, go back. What is it?
Yeah, I mean,
Here. So it's a kind of, it's a quantum version, non-commutative quantum, whatever you want to call it, version of conditional entropy. Conditional entropy would be S12 minus S2, right? But what I want to do is mix up the quantum measurement and the classical definition of entropy, which is simply the trace of rho log rho. But except these now become, well, I do that, and then I take the classical entropy, or the classical sum of those entropies. Okay? That's the definition. Is that the question?
yes.
Okay, well that's it. And now I just imagine that these sums, all these sums just become integrals. Okay? Yeah. So you see, I'm taking expectation values in one space, computing the entropy in the second space, and then integrating over the classical, what's left of the classical variables. And I'm doing the same thing in Fourier space, the same row. And comparing these two kinds of entropies. And the theorem is that this is bigger than the quantum conditional entropy. But you see there's a lot of entanglement in here, in the sense that if this thing does not separate into quantum and classical components, it's all mixed up the way it's defined. And now the overlap between the eigenfunctions and I said this before, between the eigenfunctions in the Fourier basis, which are even, and the x basis are just, as you all know, e to the ikx is the overlap between the k space and x space, and that's equal to 1, so the c is just 1. It's 1, so the log of c is 0. Okay, so it takes I mean, it's weird. I know it's weird. And it'll take for a while to settle down inside you. But the point is that there are things you can do besides just talk about entropy of entanglement. You can also talk about entropy and the uncertainty principle, and how the uncertainty principle gets messed up if you have entanglement between two sets of observables. Okay. All right. Can I go on, or does anybody have a question? No questions. My goodness. Okay. So now the last topic I think I've got time, right? I should certainly do have time. We started 10 past, yeah. Huh? What? Who's? Okay. Now, so finally, I'll end with some amusement. This is amusement. This is with Eric Collin. That's Eric over here. And so here's what happens if you try to compute entanglement in a sort of silly case, but just an illustration of what you can expect to get. It's just to show that things are not more simple or more complicated than you might think. Depends on your point of view. Anyway, so let me start with the following statement. Bosons are sometimes thought to be more complicated than fermions. Why? Because they can condense. But from the point of view of entropy, this is not so, of entanglement. Condensed bosons are, of course, in a product or coherent state. That's what it means to be condensed. The wave function is just a product of wave functions, one for each particle. And this thing is not entangled. in any sense of the word entanglement. It's just as unentangled as anything can be. On the other hand, fermions are always entangled by the Pauli principle. They can never get away from each other. And they cannot be in anything like this kind of state, of course. So our goal is to quantify the minimum possible entanglement, and as folklore might suggest, show that pure slated determinants give the minimum entanglement. This is what you might guess is the analog of the condensed boson state. Yes?
Quick question. So we understand Pauli's exclusion principle, but to say that they're always entangled, I mean, it's true that you can't put them in the same state, I understand.
Yeah,
but
right.
How do you bridge the gap to say that they're always entangled?
Well, because they cannot be in the non-entangled state. What is the non-entangled? It's this. They cannot be in this kind of state. So you'll see, if I start applying the definitions, we're going to find some minimum entanglement, and it's not going to be zero. And it comes just from the Pauli principle.
Would it not be that we could have two fermions that have not interacted before? And
They're there because of the Pauli principle. If you switch them around, you get a minus sign.
Yeah.
So they know each other. I mean, you know, if you're willing to talk about entanglement experiments over a distance of 200 kilometers or whatever, and give some serious meaning to it, I can give serious meaning to two fermions that are 200 kilometers separated. Why not?
It's interesting because...
Yeah, I know it's interesting. Well, let me go on, okay?
Just a quick follow-up.
Yeah.
Because one rule alone that entanglement is always a byproduct of an interaction.
No.
Or at least in textbooks.
It's a statement about a state.
So you can end up in an entangled state without any prior interaction.
Yes. States are states, and they can be entangled. Yeah, that's right. You don't have to necessarily work to produce an entangled state. Okay, so our goal, this was a sort of fun exercise to see that the analog of the boson condensate is a slated determinant, in the sense that the least entanglement of a fermionic state is when the state is a slated determinant. So this is just a fun exercise to close the lectures. So now we're going to study the bipartite density matrix of two fermions embedded in a sea of n fermions. We'll just pick two of them and ask how entangled are they. Some of the results depend on n, the number of fermions, and some do not, and we'll see what they are. So here's the first theorem. We return to the quantitative investigation of fermionic entanglement. We naturally assume that H1 and H2 are the same because, of course, they're fermions, they're indistinguishable. Our first theorem expresses an extremal property of slated determinants for the entanglement of formation. So here's the theorem. You take any fermionic state, rho 1, 2, for two fermions. You look at it. All you know is that they're fermions. You don't know anything else. Suppose that the range of rho 1, 2 is contained in the antisymmetric tensor product. So in other words, the wave functions we're going to look at are antisymmetric wave functions. That's what it means to be a fermion. But I want to think of this as being in the state, in the Hilbert space H tensor H. I'm just looking at a special subspace, namely the antisymmetric vectors in this space. But the space itself is just two copies of the same Hilbert space. And I compute the fermionic entanglement following the entanglement of formation, following the definition. Remember what the definition is, just to remind you, this is just an exercise in definitions. The definition is you take the state, whatever it happens to be, you write it as a sum as best you can of products, and then you compute the entropy of one factor, and then you add them up again. And lo and behold, what you end up with is log 2. So that's the theorem. That's the minimum that you can possibly have, and it's not 0. And there's equality here if and only if rho 1, 2 is a convex combination of pure slated determinants, i.e. the state is fermionic separable. Let's put it that way. That is, it can be written as not as a simple product, but as an antisymmetric product, a sum of such things. That's what I mean by fermionic separable, and that's the terminology that's used in the literature. There is a literature on this question, by the way. I'm not inventing it out of whole cloth. But the bottom line is that slaters, or combinations of slaters, minimize this entropy and this entanglement of formation and give you log 2. Another question.
Just to clarify, this H Hilbert space, is that supposed to be just a single fermionic Hilbert space?
Yeah, H by its little, one of these H's is just the space of one particle, say square integrable functions in a box or what have you. Okay. So this, and I'm looking, and in this space of both the two particles, there's the antisymmetric functions. They're also the symmetric functions. And I'm looking in this subspace, and I'm trying to minimize the entanglement. There will be an entanglement just from the fact that they're fermions. Okay? Just following the definitions. So the entanglement of formation that restricted to this antisymmetric sector is, I can define this to be the actual entanglement of formation, whatever my state happens to be, minus log 2, because log 2 is the minimum it can be. And this definition of entanglement for fermions, for two fermions, I will call the fermionic entanglement. And it's a faithful measure of entanglement. Why? Because it's 0 if and only if I've got a sum of slated determinants. Yes, sir.
You said that EF is larger than LN2. Can you use that entanglement, for example, to produce bill pairs? Can you use this non-zero?
Yes. In that sense, it's, well, let's see. No, because Bell pairs are maximally entangled, and this thing is not necessarily maximally entangled. So I'm not exactly sure. The Bell pairs are defined, of course, for C2, and this is not for C2. So I'm not completely sure. So let me bow out, because I'm not completely sure what the answer to your question is. But it's a good question. Stay with it. Okay. Any more? All right. So that's what you get. I mean, you know, people talk about entanglement. It's good once in a while to be face to face with an actual calculation. Here's a calculation. Okay. Now, we all know subadditivity of entropy, which is the same thing as the positivity of mutual information. I'm just repeating things that I've talked about before. And that equality here, that is, you get 0 if and only if rho 1, 2 is a simple tensor product of a rho 1 and a rho 2. And of course, this cannot happen for fermions because they are connected. You can't have a simple product. So I look at the maximal information for a fermionic rho 1, 2. How small can this be? And the statement is, it's at least the logarithm of 2 divided by 1 minus the trace of rho 1 squared, whatever that happens to be. And so this is not 0. And it's equality, there's equality if and only if the n-particle fermionic state is a pure state Slater determinant. Not a convex combination this time. It really has to be one Slater determinant. And then you get this as a lower bound, and it's not 0. And that's the smallest you can have for fermions for the mutual information. So again, Slaters minimize. So the Slated determinant, in some moral sense, is playing the role of the condensed bosonic state. Now, it isn't really condensed, but that's measured in terms of entanglement. That's what it does. So for n fermions, rho 1 and rho 2 are, of course, equal because they're fermions. And that's 1 over n times the identity, if there are n of them all together. And this is a non-trivial statement. Does everybody know this statement here? It's a very important statement. If I have n fermions, and I look at the one-body density matrix, I look at one of them, it's got a density matrix, right? Then this density matrix cannot just have eigenvalue 1 and the rest 0. It cannot do that. It has eigenvalues 1 over n. That's why you need, that's what you would get for a Slater. Okay? The eigenvalues can never be bigger than 1 over n. That's characterizes fermions. Okay. So here's so in this case, S1 and S2 are log n, and that's why I said some theorems will depend on n and some don't. If I look at a one-body density matrix for n fermions, the eigenvalues are 1 over n. No bigger. Okay, so now let's talk about squashed entanglement. That was the second definition I gave. And here's a bunch of conjectures. We don't know the answer, so if you want to write a paper on this subject, here's your opportunity. I think everybody should go home with a problem. So here's a problem. We conjecture that the minimum squashed entanglement occurs for Slaters, just as the entanglement of formation did. We don't know how to prove that. We conjecture that the squashed entanglement for Slater is given by this formula. We don't even know how to compute the squashed entanglement for a Slater. So let me repeat that statement. The Slater determinant, everybody knows what that is. We have a definition for squashed entanglement. Remember how it goes. You add a third Hilbert space and you try to minimize this SSA combination of terms over all choices of the third Hilbert space, and you call that the squashed entanglement. Okay? We don't know how to compute it. We think the minimum value of a squashed entanglement, for Slater even, if I give you the state, I give you the Slater state, we don't know how to compute the squashed entanglement. It's just hard. But we know it could be at least this small, and we think this is the right answer. That is, it's essentially 1 over n. It's very much smaller than the entanglement of formation, because for large n, this thing looks like 1 over n, or 2 over n or something. And we think that's what the squashed entanglement for Slater is. So here's a nice calculation you can do. You can go back to the definition, you can remember what a Slater determinant is, and you can try to figure this out. But it's at least this small. We think it's optimum. So we don't even know that, and we think that this squashed entanglement over all fermion states is given by the Slaters. Serious homework. Okay? So at first we thought, and this is a good lesson, at first we thought, I guess I have to stop, at first we thought that the minimum was the same as the entanglement of formation, namely log 2, and it's much smaller than that, something like 1 over n. This is grossly incorrect. The minimum is at least as small as the value just mentioned. Here it is again. And it depends heavily on n. And how do you get it? Well, you get it in this very funny way. You take a Slater of 2, well, let's see. You take a Slater, n-particle Slater, which is pure state, and gives us rho 1, 2. And then we take rho 1, 2, 3 to be the mixed n over 2 particle reduced density matrix of the Slated state. That is, instead of thinking of the Slated state, the state as coming from a Slated state which has zero entropy, think of taking the n/2 particle reduced density matrix of the Slated state of n particles, which is a complicated beast, and think of that as your state for the n fermions. And if you do the computation, you compute all these numbers, you end up with this. And I think I have to stop. So let me stop now because, well, I think I'm out of time, but there's something about, I wish I had a little bit more time. I would tell you about Yang states, these superconducting states, but I Marlon, who was over there, who helped me a lot with preparing the slides and made very many valuable criticisms and suggestions, and I owe a lot to him for that. And thanks for listening.
Questions? I know that like, in quasi-particle states, say like the condensed hierarchical fractional quantum Hall state, where you have sort of certain quasi-particles condensed, is necessarily a state of the underlying fermions? Or, I mean, it's a state of the underlying fermions.
Yes.
But do you know if people... So I don't know if it makes sense to talk about what's the minimum entanglement of a quasi-particle state, because maybe you can just reduce it to the underlying fermions. But do you know if people have...
No, I don't know. Not to my knowledge. I mean, but I'm not an expert, so the answer is no, I don't know.
Okay.
Yeah.
So was there a, I'm just curious, was there a reason you didn't discuss topological entanglement entropes?
I'm not going to, I have nothing to say about that. Yeah.
Is it meaningful to distinguish entanglement between particles and entanglement between orbitals? Well, let's say I have like two orbitals, each with a fermion. Then if I look at the occupation basis, each orbital has one particle. Right? So I would naively say that between the orbitals, there's no entanglement. And yet, this...
As I said at the very beginning of the first lecture, when you talk about two Hilbert spaces, they can refer to all kinds of things. The theory is general, but the Hilbert spaces can refer to two chunks of a lattice, or in which case we're worried about this area law. It can refer to 2 degrees of freedom. It can refer to all kinds of things. And yes, it's meaningful. And what you do with it physically, well, that's another question. That remains to be seen. But remember, way back, until very recently, not so far way back, until very recently, nobody thought entanglement was of any use whatsoever to physics. It was sort of some kind of curiosity over there that philosophers worried about. It's only recently that people started to take this stuff seriously. So, therefore, I think one should look at all possible ways of looking at entanglement, degrees of freedom, and how they're entangled. Not just chunks of a lattice or black hole. Yeah.
I want to come back to the question that was asked over here about, say, swapping that entanglement out of the fermionic system. Like if you had 2 fermions and then you had 2 unentangled qubits, you couldn't really swap the entanglement into these and have 2 unentangled fermions, because then
No, you cannot. No, you,
so it's sort of, in a sense, it's stuck. Right? It's stuck in the system.
Yeah.
So,
So
I guess the question was, there's this ln 2, which is the lower bound in the entanglement of formation. The question was, is that usable? I guess the answer is no.
the answer is, well, no. The answer is no. Yeah, probably. I mean, that's a very valid criticism. And you find this in the literature. I mean, you're not the first to make it. That since you can never squeeze this out, I mean, it's there because they're fermions. You can never get rid of it. Maybe you shouldn't count it at all. But so that's why I presented this as an amusing exercise in using the definitions. And I wasn't presenting it really as something you could use physically. But who knows?
And then maybe an unrelated follow-up is that if you talk about bosons in the symmetric subspace instead of just being things that can condense into a product state, is there?
That's an example of. Oh, I see what you're. Go ahead. Finish the sentence.
So that they're symmetric. Is there something? Can you redo this analysis?
No, you'll get zero. If I ask, in all these questions I've asked, what is the minimum possible entanglement? The answer for bosons is zero. That end of story as far as this line of research goes. You could ask other questions. We've asked the question, what is the minimum? And the answer is zero for bosons. Then that's it. Anybody else? You're all worn out. Okay. See, the advantage of being the last speaker is I don't have to stop, right?
Oh, you're the second to last section. Let's thank Elliott again. And please come back at 1:30 for Professor Maldacina's last topic.